We have already talked about similar figures before, but now we're going to talk about 3D similar figures. So if a solid is similar, that means that we have two solids that are the same type of solid. So if it's both cylinders, both pyramids, etc., and they have a common ratio of our corresponding linear measures. So the sides ratios are the same, or the heights are the same, the radius measures, the ratio is the same. And our scale factor means that it has a common ratio from one solid to the other solid. When we are looking at certain shapes, we know that all cubes are going to be similar to each other because all the sides are the same to begin with, and all spheres are going to be similar because the only pieces that we can compare are the radius, and since there's only one measure we're comparing, then of course they're all going to be the same ratio. In number 1 and 2, we are going to go through and figure out now if these two solids are similar to each other. So we need to make sure that all the ratios comparing the sides, heights, etc., lengths will be identical to each other. If I pair up my 12 over the 9, we can pair up our 16 with our 12, and we can pair up the 4 with the 3. 12 over 9 becomes 4 over 3. 6 over 12 becomes 4 over 3. And my green one of 4 over 3 stays 4 over 3. So they are all the same ratio, so yes, these are similar. Now on number 2, I want you to do this yourself. So pair up your radius with each other, and then also pair up the heights with each other and compare those ratios and see if they are identical. If you paired them up like so, we get a 2 over 1, and then 15 over 10 becomes 3 over 2. Since the sides are not the same ratio, these are not similar to each other. On to the next part with scale factor. If we don't even have our shape, the scale factor, when we compare this, scale factor is really the sides, so that's like A to B. If we are comparing the volume ratios, we need to take in consideration that that is cubed. So A to the third is similar to B to the third. So we're going to use that in this chart to fill it out. If we have the scale factor of the sides, that means that our volume ratio, we need to take each of those and we need to raise it to the third power. So that gives us a 27, and 125 would be the ratio between our volumes of our two shapes. So if we go backwards on that, we have to take the cubed root of each of those numbers. So the cubed root of 8 is 2, so that means 2 times 2 times 2 is 8. And the cubed root of 27 is 3, because 3 times 3 times 3 is 27. So that means our ratio of our scale factor, so the ratio between our sides, would be 2 to 3. So this next one I want you now to do on your own. Tell me, what is the scale factor going to be if this is the given ratio? The cubed root of 8 is 2 again. The cubed root of 125 is 5, so you should have put in 2 to 5 as your scale factor. We are going to use the idea of this chart to help us find the scale factor of a similar figure if we have a scale factor. So the cans that are shown in our picture of these peaches have the scale factor of 87 to 100. Now remember, that's the sides themselves. It's not after they've been cubed. This is just the regular scale factor. And we need to use that to find the volume of our larger can. If we start with 87 over 100, we know that that is the sides, not the volume. And if we need to find the volume ratio, that means that we need to cube each of those numbers. Then we know for the other side it needs to be small over large, and the volume numbers we have is for the small one, so that goes on top. And then the volume we are solving for is the large can. And now we really just need to cross multiply. But first we need to simplify those numbers. When we raise each of those to the third power, these are the numbers we've got, and yes, they are quite large. So once we cross multiply, we need to multiply that 1 million times the 28.27. And then we need to divide both sides by the 658,503. And that gives us our volume of 42.93070798. And we are going to round to the nearest 100ths or hundredths. So we're going to put 42.93, and this would be inches cubed, will be the volume of that larger can. So now we're going to do the same thing. We're going to use the same idea for number 5. If we know that our two pyramids are similar to each other, we need to work backwards and figure out what the scale factor is. So if we say it is P to Q, that means P is on top, Q is on the bottom for all of our numbers. So in our ratio, they give us the volume of P is 1,000, and the volume of Q for the bottom is 216, and we need to take that and go backwards, so we need to find what the scale factor is. It's almost like our chart up here. If we start with the volume numbers, we need to go backwards for the scale factor. So we took the cubed root each time. So if we take the cubed root of 1,000, we get 10. If we take the cubed root of 216, we get 6. And now, of course, reduce it like we usually do. So divide both of those by 2. So we would get a 5/3 would be our scale factor from P to Q. Or you could write it like so for your scale factor. Now for the last 3 questions, if we ever adjust one piece or one length in our figure, we need to know what happens to the volume, or how does the volume change. So first you need to know what is the shape. So here this first one is a cone, and that means that our volume equation is capital B times H. Now remember, because it's a cone, we know that the base is a circle, so that's really pi r squared times h. So you always want to reduce it and simplify it like that so you can work with it a little bit more specifically. Now if our radius is tripled, right now it is a 1r, but I need to change that so that my radius is a 3r instead, but everything else stays the same. Now if I simplify this, we have to square, think back to Algebra 1, we have to square both parts inside of that. So we get pi, and now that becomes a 9r squared, and then my h stays the same. So if you notice, there is a 9 here now, versus before there was just a 1, so that means it is 9 times larger. That my volume is 9 times larger than what it started with. And that's only because the radius was tripled, and the radius in our equation has to be squared, so I'm really squaring 3 to get my 9. Next, we are dealing with a pyramid, so let's start with our pyramid equation. And that would be 1/3 capital B times H, but because it is a rectangular pyramid, that means that that area of the base is just going to be length times width, and then times our height of our pyramid. So that L and W is switched. Now we need to multiply the length of, or the length is being multiplied by half. So I need to squeeze, right now it is a 1L, but now I need to put a 1/2 L in place of it, but everything else is staying the same. So notice the only thing different between those two, and I don't have the square to have to deal with, so all I have is the 1/2 compared to the 1, so that means my final answer is going to be half as large. For this very last one, I want you now to set it up on your own, so let's get you started though. If it's a cylinder, remember that you start with your B times H, and your B is pi r squared H. So now I want you to adjust your height. Your height is being doubled, and I want you to tell me now how will the volume change because of that. Your height to begin with is a 1h, and if we need to double it, everything else stays the same, but now in place of it, I am putting a 2h because I am doubling it. Now if I simplify it, it still stays a 2 because it's not squared or anything else. So if it changes from a 1 to a 2, that means you should have chosen that it was 2 times as large as the original volume. So it's 2 times larger.